Hi everyone, I'm Giovanni. I'm a second-year PhD working with Stuart on gravitational lensing, and today I'll talk to you a little bit about what gravitational lensing can do to some statistical properties of high redshift galaxies, in particular their UV luminosity function. So, quick review of lensing. You have on the left a source, let's say it's a galaxy, on the right it's us. You can take a bundle of light from the source and get to our eyes. Let's now introduce a third object in the middle. Let's say it's another galaxy. We call it lens. And now the same bundle of light that we got before will be deflected by the gravitational potential of the lens in the middle, not coming to our eyes. Not only is lost, you can imagine that there will be another set of bundles that will be focused on us through the deflection of the lens. And maybe there is more than one. And this is, in essence, lensing. A bit of notation we call source the background object, which lives in the source plane. The lens is in the lens plane, and the image is formed in the lens plane. And the two, the source plane and the lens plane, are related through the so-called lens equation, which looks simple but is very nonlinear, and it relates the position in the source plane to the lens plane through the deflection angle. And from this very quick sketch, you can already see that there is some sort of magnification between the image and the source. And let's call magnification the ratio between the angular area of the image and the source. Now, probably you're familiar to this example of lensing in the bottom right. In the middle, you see in yellow the lens galaxy. And all around it, there is a background blue galaxy, which is stretched along what is called the Einstein ring. And if we map this position, which is also called critical line, where the magnification diverges, back to the source plane through the lens equation that I showed before here, if we go back to the source plane, we get this shape of a caustic. Now, what's important for the sake of my discussion today is that the closer you put a source to the caustic, the higher magnification it gets. Now we can ask ourselves, if I put random sources in the source plane, what is the probability distribution of their magnification? And if I take a spherical lens and a point source, this is what you get. It's a power law. And the interesting thing now is that if you introduce a finite size source, you get a cutoff in the magnification. So there is a maximum magnification you can get. And the intuitive reason is that you cannot get asymptotically close to the caustic anymore. At some point, you cross it with the effective radius of the source. Okay, so now for a little bit more precise, we define the lens as a singular isothermal sphere, and we take a point source is the dashed line, and finite size sources here in a-dimensional quantities expressed as a fraction of the Einstein radius. And we see that the bigger the source, the smaller the maximum magnification I can attain. And now if we introduce the lens ellipticity too, also this contributes to getting a smaller lens, maximum magnification. So in the right panel is the singular isothermal sphere. In the middle panel, there is a singular isothermal ellipsoid with the ratio of the axis, which is 0.7, and on the left, 0.4. Cool. So this is the lensing introduction. Let's move to luminosity function. Very quickly, luminosity function is the number of galaxies per unit volume with luminosity in a certain beam range. And it's often parameterized with a Schechter profile, which has a power law for the faint end and an exponential cutoff at the bright end. Here I'm showing some results from Bowens et al. 2022 for redshift 6, 7, 8, and 9 galaxies. And those are quite well represented by this Schechter function, but I want you to notice on the very left of all these panels, so on the bright end, so for magnification above -22, brighter than -22, we start to see a deviation from this Schechter profile. Going back to lensing a little bit, what is the probability of seeing a lens galaxy if we look at random line of sights? So I very carefully mask the actual integral, but the idea is that you can get the sense from given the population of lenses. So the strength of a lens is characterized by its mass, and a proxy for the mass is the velocity dispersion. So if we get the velocity dispersion function of the galaxies between, let's say, redshift 0 and 2, which is where lenses are more effective, we can get our sense of how the distribution of lenses and their strength is. So if we integrate this through the velocity dispersion and the redshift between us and whatever redshift we want to probe for the source population, and we multiply this by the area in the source plane, but which is produced by these lenses, the fraction of the total area in the sky at that redshift and the area of the source plane that we stitch together is the probability of lensing. We can multiply this by the, so the term on the left is the so-called optical depth, lensing optical depth. And on the right, we have the integral over magnification of the luminosity function and the magnification distribution. This is a bit less intuitive, but you can think it, looking at this GIF as a convolution. So you have the luminosity function, which is in white, a Schechter function, and you're convolving it with the magnification distribution, and the faint end is very much the same. While at the bright end, we get a bump, which is look much closer to a double power law than the Schechter cutoff, because you are bringing the fainter, intrinsic fainter galaxies to apparent brighter magnitudes. And this is what happens. So this has been done throughout the years by the people that I cited here, amongst others. What I did is introducing extended sources and elliptical lenses. So here you see that if you change the kernel of the convolution, you are getting intermediate solution between the double power law of a point source and the intrinsic Schechter. And again, if you change it to a smaller one, you get the same, you get closer to the intrinsic Schechter. Okay, now there is some problem that arise because you cannot anymore separate the two integrals between each other, because now magnification, the demagnification distribution is a function of the lens redshift and the velocity dispersion of the lens to scale it to the source plane. But let's say we can do that, and it's also a function of the ellipticity of the lens, but we can integrate over the ellipticity that we see in the sky. And we get this. So this is some data points for galaxy luminosity function, mainly for Americana and Bowens, redshift 6. And overplotted, it's some result from my model. So in white is the intrinsic Schechter. In green is the point source solution. And in various color and dashed lines is a combination of solutions for different choices of parameters for the luminosity size relation. So R0 and L0. So this could be, well, you can see that the data point is not constraining much here, so especially the right one. But in the future, there could be an interesting way to probe the intrinsic size of the sources through an indirect measure of the lens, of the lensing of the luminosity function. And here I just plotted another graph with a similar result in solid line dashed and dotted is redshift 7, 11, and 14. And I'm overplotting also the phase space that will be able to probe different surveys. So GWST is very good at going deep in flux, but there's a small comoving volume per pointing. While the Roman space telescope will be, and the Euclid 2 will have very large comoving volumes. And these are necessary to probe the very low probability densities of very bright galaxies. So to summarize, okay. The source size and the lens ellipticity introduce a cutoff in the magnification distribution. Convolving this with the intrinsic Schechter function of the luminosity function gives a sort of double power law-like profile. And this could be used to probe the intrinsic size of the source population through fitting the data between the UV luminosity function at high redshift. Thank you. The paper is on MNRS.